Hello my dear friends, hope all of you are doing well. So today I am going to discuss on new chapter is called the moving charges and the magnetism. It means how the charge moves through any matter producing the magnetic field. So electric field and the magnetic field both are interconnected. So let's dive into today's topic. So today's topic is moving charges and the magnetism. Both electricity and the magnetism have been known for more than let's say around 2000 years. In 1920, the scientist Hans Christian Ørsted, a Danish scientist, established the relation between the electricity and the magnetism. He concluded that a current carrying a wire through a wire produces a magnetic field around it. From the figure one can see that a thick insulated copper wire here, and it is carrying a current and connected to the battery, and a compass needle is placed under the wire. You can see there is compass needle is placed under the wire. The deflection of the compass needle is in the opposite direction when the direction of the current flow is reversed. And when the current is switched off, you can see there will be no deflection in the compass needle. There will be no deflection. So the conclusion what he made, Sir Ørsted, was like the deflection of the compass needle whenever there is current in the wire, and it shows that a current carrying wire produces a magnetic field around it. So a current carrying wire means the charges are moving. I mean the electron. So moving charges causes the magnetism in its surrounding place. The laws which are obeyed by both the electric and the magnetic field was discovered by Sir James Maxwell in 1864, and then in parallel it was also realized that light is an electromagnetic wave. So far we have came across a long way in the 20th century to understand the electromagnetism, and we are trying to investigate the production, amplification, the transmission and the detection of the electromagnetic waves. So now we'll present a current or the field coming out from the plane as this sign, and a current or the field going deep into the plane will be represented by this sign. So now discuss what is the magnetic force before starting our discussion on the magnetism. So what is the magnetic force? In previous we have discussed the interaction of the two charges, where one charge capital Q is fixed in the space and it has the higher value of the charge, and it is the source charge producing an electric field E vector in the space. So here also if I compare with the electric field like previous one, the capital Q is the source charge which is fixed in space producing an electric field at a distance of small r vector in the space, which will be E vector is equal to capital Q divided by 4 pi epsilon naught r square r cap, where r cap is the unit vector along the r direction, and electric field also vector field. And a test charge of small q interacts with this electric field. So what will be the force on the test charge of small q? F is equal to QE. So it will be like F equal to QE. So it will be capital Q small q divided by 4 pi epsilon naught r square r cap. The electric field is said to be the force exerted on a single positive 1 unit of test charge, as we have learned before. The electric field can also be a function of time, but here we are taking the electric field which do not change with the time. Similarly, like the electric field, the magnetic field is in a region around a magnetic material or a moving electric charge within which the force of the magnetism is the acting one. So magnetic field is, the region one in which the force of the magnetism is acting. So we can write like the magnetic field is the region around a magnetic material or a moving electric charge within which the force of the magnetism is acting. So we can define the magnetic field like the magnetic field will be a function of its position BR, and a magnetic field has several basic principles like identical to the electric field, like different values in the space, and it may also have the time dependence. And the magnetic field also follows the principle of the superposition, which states that the magnetic field for several sources is the vector addition of the magnetic field of each and individual sources. Now we will consider the force that a point charge must feel in the presence of both electric and the magnetic field simultaneously that are present in the space. This brings the concept of the Lorenz force, the force that is named after the Dutch physicist Hendrik A. Lorentz. So this is the Lorenz force. A point charge, suppose Q, that is moving with a velocity v and located at the position vector of r at any instantaneous time of t, suppose. So there is simultaneously electric field and magnetic field are present. So electric field and magnetic field both have the spatial dependence. So electric field is a function of the r, and magnetic field is also taken as a function of the r. So the force on the charge q due to both the electric field and the magnetic field can be written like F is equal to the total force is equal to the sum of the electric force plus the sum of the magnetic force is equal to Q times ER, that is Q times E is electric force, and the Q times V cross B, where V is the velocity, B is the magnetic field, velocity, magnetic field. So Q times V cross B is the magnetic force, Q times E is the electric force. So the sum of the both two are called altogether the Lorenz force. The second term is due to the magnetic force and it is acting perpendicular to both the velocity. You can see this is a V cross B is a cross product. So the magnetic force is acting in both the perpendicular direction of the velocity and the magnetic field. Now in terms of the angle phi, we can write it like, if phi is the angle between V and the B, velocity and the magnetic field, we can write the F magnetic is equal to QVB sin phi. So what is the conclusion? The force becomes zero if V and B are either parallel or the anti-parallel. You can see if V and B are the parallel or anti-parallel means the angle between them will be either 0 degree or 180 degree. So it becomes 0. And the second conclusion will be like force on a negative charge is opposite to that of a positive charge. Obviously it is from the sign. When the velocity is 0, there is no magnetic force because E times V cross B, if the velocity is 0, there will be no magnetic force. And if phi is 90 degree, we can write it like F is equal to BQV, sine of 90 degree becomes 1. So we get the expression for the B like B is equal to F by QV. Now if I consider Q as 1 coulomb, the charge of the moving particle, as 1 coulomb, the velocity is 1 meter per second, the force acting, the magnetic force acting on the particle is F is equal to 1 Newton, then the value of the B, that is the magnetic field, becomes 1 SI unit. Now you can see this is the two kind of unit is there. One is the SI unit, one is the CGS unit. So in SI system, the magnetic field has the unit of Tesla. It is named after the scientist Nikola Tesla. We can write it also like Tesla is equal to Weber per meter square. In CGS, we can express the magnetic field units in Gauss, and the relation between the Tesla and Gauss is written here. 1 Tesla is equal to 10 to the power 4 Gauss, or in reverse, 1 Gauss is equal to 10 to the minus of 4 Tesla. The charge particle accelerators like the cyclotrons make use of the fact that the particles move in a circular orbit when V and B are at the right angles. Now we'll try to understand how the magnetic field is produced in the surrounding due to a current carrying wire. From the previous experiment of Sir Christian Ørsted, we have seen when a magnetic needle or the compass is placed below a current carrying wire, it deflects. So there must be any force acting on the magnetic compass. Now from the figure we can see, if you can see from this figure, if the current I is moving in the upward direction, the direction of the generated magnetic field will be the tangent of the produced imaginary circular loops. If I consider some imaginary circular loops perpendicular to the plane and the current is passing through the just penetrating the plane, so every time the magnetic field direction will be tangent to this imaginary circular loops. We can also understand this fact using this right hand rule also, where the thumb points the direction of the moving current, the thumb directs the direction of the moving current, while our fingers that are wrapped around, you can see this the direction of the fingers that is wrapped, it directs the pointing the direction of the magnetic field. So our wrapped fingers directs the direction of the magnetic field. So the magnetic field direction, it comes from the right hand rule. The direction of the wrapped fingers indicates the direction of the magnetic field. If the magnetic field is coming out of the plane, it is represented by dot, you can see here. It means the magnetic field is coming out of the plane. And while it is going deep into the plane, we can represent it like as the end of the arrow, as shown in the figure. You can see here, it is shown here. So if the magnetic field is coming out of the plane and this is in this side, magnetic field is going deep inside the plane. Now as we all know that the electric current is ordered movement of the electric charge, so and a current carrying wire in a magnetic field must therefore experience a force due to the magnetic field. So now we'll try to calculate how much the magnetic force that will be felt by the current carrying conductor in the magnetic field. So magnetic force on a current carrying conductor. Now let's have some fun. Try to speak quickly this sentence. And current carrying wire carrying current I. So you can see from the figure, this is the wire, the current I is passing through it, and the magnetic field, this is the same in everywhere, and this is the direction of the magnetic field, and at any point it is making an angle theta with the wire. So I choose some small element of the wire and I just make it I just zoomed this part only, so you can see this is the cross-sectional view of the wire, and the wire has the cross-section of A is the cross-section of the wire, DL is the infinitesimal length, I have considered one very small length, and Vd is the drift velocity of the carriers, I mean the electron here, and B is the uniform electric field that is present here, and N is the number of the charge carriers per unit volume. So again I am telling this is the A is the cross section of the wire. I have chosen only some infinitesimal length of DL, and B is the uniform electric field, and Vd is the drift velocity of the carriers. Here it is the electrons. So now you can see that the current in the length element of DL, we can write it like I is equal to NEAVD, where N is the charge carrier per unit volume, A is the cross-sectional area, E is the electron charge, Vd is the drift velocity. Now magnetic force due to the presence of the magnetic field B on each of the charge carrier that we have learnt before, just before, but it will be E times Vd cross B. This is for the single charge carriers. The magnetic field that every charge carrier will feel due to the presence of the magnetic field B, that is E times Vd cross B. Now for a total number of charge carrier NaDl, so I have chosen some elementary length here dl. So in this length dl, there will be the total number of charge carriers will be NaDl, because ADL is the volume of this elementary length and N is the charge carrier per unit volume. So NaDl is the total number of charge carrier that are present in the elementary length of dl. So for a total number of charge carrier NaDl in elementary length dl, the elementary force, if I have to calculate dF, that will be the total number of the charge carriers times the force every charge carriers which are feeling in the presence of the magnetic field B. So it becomes the elementary force dF is equal to NaDl times E times Vd cross B. Now you can see from this figure that the dl vector and the Vd vector, I mean the elementary length, we can take the elementary length as a vector one, because for only that part only it has some specific direction. So the elementary length and the drift velocity are pointing in the same direction. So we can, as dl are parallel to the drift velocity, so dl can be taken as dl vector. So we can write this expression like dF is equal to NeAVD dl cross B. So NeAVD, I will replace NeAVD by I, that means the current that is passing through the wire, so it becomes I times dl cross B. So this is the magnetic force on the section of the wire. So it is the net force on the charge carriers, I times dl cross B. To determine the magnetic field on an arbitrary length of L for an arbitrary shaped conductor of length L, we need to integrate. So the force become dl, if I integrate it, it becomes L. So the force become I times L cross B, where we need to take that the magnetic field is uniform. So my friends, I am concluding today's discussion here. If you are new in this channel, please do like, share and subscribe us, and make your valuable comments. Stay tuned and keep supporting Invisible Threads. Thank you.